Okay, good afternoon, everybody. Yeah, I forgot to bring a comic. So, we have.
The integral of 1 over cabin.
What's the integral of 1? Oh, log cabin, right?
Wrong. It's houseboat because it's a
C.
houseboat.
Oh, a log cabin plus a houseboat. Okay, you all didn't get that right. Thank you, Ellen, by the way, bonus points. So then for today is then we'll finish up this last piece of 6.4. I'll kind of cap off the semester by providing kind of a cool example of this business that comes actually from 6.5. But remember, you're not responsible for 6.5 on the upcoming final exam, which, speaking of, remember, don't show up here. Friday morning, 8 o'clock, you should be at Fisher 135 if you want to take the final. That comes from 6.5. That kind of caps a lot of the stuff we've been working on. And then we'll take the rest of the time that remains to review for the final exam. You don't already have some scratch paper or something on it? I'm going to ask for a little audience participation. So try some of these on your own. That's too much to chew at once. So let's start there. So I have maybe two or three things here to review for the final exam. I picked ones that I guess are probably further back in your history than some others. So this is one that goes back a ways. So recall that if a transformation T from Rm to Rn is a linear transformation, then you can find a matrix that makes it happen. Call that matrix A. So we take an input vector in Rm, we multiply it on the left by this matrix, and it will go to Rn. Whatever the rule is for this transformation that maps these vectors to these vectors, it can be described through matrix multiplication. And we found out how to find that matrix. This just says that the matrix has as its columns the images of the unit vectors. Right, remember what is E1? Yeah, E1 is the unit vector with 1 in the first position and zeros everywhere else. E2 is the unit vector with 1 in the second position and zeros all the way down, and so on. So that may remind you how to find these matrices. Okay, so take a moment. Here's a transformation. One of these is the correct matrix for it, see if you can come up with it. Okay, so by the way, notice here, just to take care of some notation, this is going from R what to R what? Good. It's a transformation that goes from R3 to R2. The inputs are in R3, the outputs in R2. Okay, so that okay, I won't give the waiting answers. Let's do the clapping thing again. Okay, so Walt, I'll just clap randomly. I'll tell you where to clap. Okay, so we'll clap in the affirmative. So if you think it's the matrix I'm pointing to is the correct answer, then clap. Okay, so go. Okay, either no one's participating or everyone's right. That obviously is ruled out because the columns of A are the images of vectors, right? But the images of the vectors we only have 2 spots, so that's the wrong size anyway. So good. Okay, try this one. All right, good. This one. No one clap for this one because I said good here. Everyone clap. So yeah, this is the right one. Just check. So E1 1 0 0 goes to 1 plus 0 1 minus 0. So 1, 1 is definitely the first column. E2 is 0, 1, 0. So that's 0 and 1, and that's 0 and 0. So 1, 0 is that column, that's good. Now put in E3 into the machine. X1 and X2 are both 0, X3 is 1. So the top coordinate is 0 plus 0. The bottom coordinate is 0 minus 1. So, yep, 0 minus 1, that's right. So that's good. Some more questions. Maybe if this person's sitting next to you, look very smart, ask them or float your idea by. Just so one of you isn't clapping while the other isn't, and then there's an awkwardness between the two of you. Someone want to be my guest, I guess, before we clap? Onto means what? There is always an answer. That's a good way of thinking about it. So this is the matrix A, right? So we're wondering, is AX equals B consistent for all B? That's exactly what onto means. Okay, a consequence of that. So that is true if and only if A has a pivot in every row. So now maybe we'll be clapping for the right one. So again, clapping for the affirmative. Yes, it's onto. Okay, good job. Yes, you're right. Because of the second piece. That's the easy test. There's definitely a pivot in every row. It's not in RREF form right now, but this is an example of something you could waste your time on the exam. So you have your Mickey blanket next to you called your calculator, but as I already told you, all the problems on the exam can be done easily without a calculator. So my point is, don't put this into your calculator and ask for the RREF, because you can get there in one step, right? What are you going to do? Use this as a pivot, take -1 times row 2 and add it here. Right? Take -1 times row 1 and add it here. Well, that's going to be a 0, and that's going to be a -1, which is a pivot. So I got a pivot, a pivot. Yeah, there's a pivot in every row, so yes. Reminder of 1 to 1.
For every vector x is exactly
Not, okay, so for every, so AX equals B for every, not quite.
B is not unique.
Not quite, not unique. Unique's the wrong word. Okay, that's the second part. So the easy check is, yes, it is 1 to 1. No, I mean, it's not. I'm saying, well, we haven't voted yet. But if it is 1 to 1, it's 1 to 1, so 1 to 1, if and only if, okay, so A has, I heard the shortcut over here. A has a pivot in every column. But that's really because of the definition of 1 to 1, that every B has at most 1 x. So not necessarily exactly 1 x, such that AX equals B, but every B has at most 1 x, such that AX equals B. So there can be B's that are unobtainable. They have no solution x. So pivot in every column, this is the same as AX equals 0. Has only the trivial solution. Okay, but yeah, these guys down here hit on it. 1 to 1, if and only if there's a pivot in every column. Okay, so is this transformation 1 to 1? Is it not 1 to 1? Good, yeah. Okay, good. So definitely no. I mean, there's not going to be, there can't be a pivot in every column, right? There can be, you can have at most 1 pivot per row. There's only 2 rows, but you have 3 columns. Yeah, this can't be row 1.